which is first some general discussion of the decay law, some recall of the experiments, and then the decay law in the multi-channel case. So when there is not only one decay channel, but more than a single decay channel, which is basically a normal situation for decays. And then the decay of a particle which is moving. Usually we study the decay in the rest frame, when the particle, we sit together with the particle. So what if the particle is moving with respect to the observer? Okay, so the general discussion starts like that. So first thing, I mean, if we put, for instance, a box of N0 unstable particle, so even from the high school, we know that the number of unstable particles decreases according to the exponential decay law, which is the one here, where tau is 1 over gamma, h bar is equal 1, is the mean lifetime. This is confirmed in countless cases, of course. It is a very good empirical law. If I take a single unstable particle, then what I speak about, this is the survival probability. So the probability that the particle is still there after a time t. And this is this expression here. This is, of course, a probability in the sense that it is an intrinsic probability of quantum mechanics, in the sense that we can only calculate if the particle is there with a certain probability. We do not know when a single particle will decay. So this is also why actually Schrödinger used that for his cat killing machine. If we do a Taylor expansion of the exponential, of course, we get something of this type, 1 minus gamma t, etc., etc. And this is the first thing that I will say in a second, that it cannot actually be like that. So let's consider an unstable state, let me call it S, prepared at t equals 0. So in quantum mechanics, then what we actually would like to calculate is this object here, which is the sandwich of the particle, the state S, which is still there at the time t. So this is simply the sandwich of S with the time evolution operator in the middle. And the survival probability is just calculated as the amplitude modulus of the amplitude squared. Actually, there is a fantastic review by Fonda, Ghirardi, and Rimini that I quoted here about all aspects of decays. It is still, I mean, it's from 78, but it's still a very, very good summary and actually a very good level of mathematics of all these things. Well, if we look now, and this is a simple exercise that one can do at the Taylor expansion of this amplitude. So this is up to time squared of the amplitude, and this is the complex conjugate of the amplitude. It then follows very simply that the survival probability, you see, it takes this form. There is no t. So if you remember the expression here from the exponential, I should get something like 1 minus gamma t. But if we just do this simple calculation, you get that there is 1 minus t squared time a constant. So you basically see immediately that the decay cannot be exponential at short time by a very simple calculation. So it starts quadratically, basically. So at low time, the decay is 1 minus t squared. And this is actually, so it looks like this is just a simple pictorial representation. So this is the exponential law at short time, and this is actually, it should look like, as it looks like in any possible decay, because this is very general. So it starts flat, and then of course it goes down. It's 1 minus t squared. Actually, such a quadratic behavior holds for any quantum transition, not only for decays, of course, but in the particular case of decays, it is also like that. More in general, of course, this is valid for short time. More in general, if I would like to calculate the survival probability of an unstable state, the final formula for calculate that, and one can find it in the review paper of Ghirardi and Fonda and Rimini that I wrote before. So this is the expression. The survival probability is just a Fourier transform of the energy distribution. So the energy probability distribution. So an unstable state does not have a single energy, it has an energy distribution. It is not an eigenstate of the energy. And if we do the Fourier transform of that and modulus squared, this is the survival probability. And of course, if, for instance, you plug in here a Dirac delta, so if you go back to the case in which the decay is exactly, the unstable state is an eigenstate, and then it's not unstable anymore, so in the limit in which it becomes stable, then this object here is 1 for clear reasons. So we go back to a stable state, so to say. But in general, I should do a calculation of this type. So if we know the energy distribution, or the spectral function sometimes is also called, then one can calculate the survival probability. Of course, a very well-known limit is the Bright-Wigner distribution, which goes back to many years ago, I think the 30s. So if the energy distribution has this form, and this cannot be a physical form because there is no minimal energy first. So the Bright-Wigner distribution comprises energy that goes from -infinity to +infinity. So of course, so it means that it cannot be a realistic spectral function. And this is also, we can understand any physical unstable state as a minimal energy. So if we take the decay of the neutron, the minimal energy is the mass of the proton plus the mass of the electron plus the neutrino. Of the 2 neutrinos, sorry. So, and then, so let me just do a simple example. So let's modify the Bright-Wigner distribution in such a way to take into account an energy threshold. So this is just done, this is by brute force with a theta function. And let's put also some kind of form factors, some exponential here. So, and this is, so if I take into account now this energy distribution here, so I can compare it to the Bright-Wigner form, which is the dashed one, and the solid line is this function here. So one can see now that I put by brute force to say a threshold, an energy threshold, a low energy threshold. This is just for illustrative purposes. Of course, in reality, the functions are not such. There is no jump, but there is an energy threshold. And then if I do the Fourier transform, so this is the Fourier transform of the Bright-Wigners, which is an exponential, and the Fourier transform of the solid line, which is this modified Bright-Wigner, goes like that. So it starts as quadratic, as I said, as the general case should be, and then after a transient time, it is very similar to the exponential decay. Of course, if there is another thing, if one goes at very long time, the decay law is also a power law. So it is 1 over time at a certain power. It is also not exponential at long time. So at short and at long time, there are these deviations. And this is, so to say, a simple way to see that by a numerical implementation done by just changing the Bright-Wigner in this way. Are there experimental proof of that? Of course, this is, of course, an important question. In the majority of cases, we know that the decay is exponential. I mean, the exponential decay law works very well for describing the decay. I am aware of only 2 experimental verifications of the non-exponential decay law. One goes for the short time, goes to sodium atoms in an optical potential, which is accelerated. So basically, you can imagine to have a sodium atom here that then can tunnels out in this direction. And this is the decay law that has been measured. So one can see that it is non-exponential at short time. So this is actually the solution, an approximate solution of the Schrödinger equation for the tunneling. It is not exact because of the approximation. By solving the Schrödinger equation by brute force, one can really go on the data. And this is the same just at but a long time. So at a long time, you get again the exponential decay. But short time, one see that it starts quadratic. By the way, they repeated this experiment later on by also adding some measurements in between. And this is something not discussed today, but then they could verify the Zeno and anti-Zeno effect, so that you can make a state living longer or shorter, depending at which interval you make the measurement. But I will not comment on that more. What about late time? And here there is a paper that goes back to 2006, and these are some molecular objects, some rhodamine, etc. These are rather complicated molecular states that decays by emitting photons. And so this is a double log plot. When we see here this, for instance, this is this, this should be this rhodamine, if I'm not wrong. You see there is this point where the double log breaks down, and so it becomes a power law. The decay becomes a power law after this time. This is usually something like 7, 8, at least lifetimes. After that, the power law sets in. There is no more, to my knowledge, there are no more experimental proofs of that, which is something that, I mean, for something that should be so general, it is unfortunate that we only have these 2 experimental papers. Of course, it would be nice to see the deviations in simple natural system, nuclear decays or whatever, both at short and long times. This is technically difficult because usually this deviation from the exponential law in the short time are very short, and at a long time one has to wait very long when basically the sample is gone. So this is the problem of seeing these things, but in principle it should apply to any decay. So this is just a formula argument how I calculate then this probability, the survival probability actually. So the idea is that the decay function, the decay width is not a constant, it is a function of the energy. So then the spectral function takes a form, it is the imaginary part of the propagator. This is in quantum mechanics, not in quantum field theory, but in quantum field theory basically it is the same. And the imaginary part of this loop is actually the decay function, which is in the limit in which this gamma v is a constant, I go back to the Breit-Wigner and to the exponential decay. But in general, this is not the case. So this is just how the propagator is calculated. It's just as in quantum field theory, the propagator has this form, and this is the loop, and the imaginary part of the loop, because of the optical theorem of the self-energy, is the proportional to the decay width function. So, and any propagator can be written in this form. Basically, is the sum of 3 propagators, and this is the spectral. This is the spectral function. So the probability that the energy between E and E plus the E is given by ds by this function times the E. Okay, what about the multi-channel decay law? So what I said, of course, is general, but then of course the question is, so these are the 2 papers that I published on that. One is very recent. So the simple question is the following: if I know which is the survival probability, which is the probability that the state has decayed? Well, this is very simple. If the survival probability is P, the probability that the state has decayed is 1 minus P. This is obvious. By the way, there is also an interesting quantity, which is the derivative of that. So h of t, I call it, which is the derivative of the decay probability, the probability of decay, and h of t, the t is the probability that the decay takes place between t and t plus the t. So it's the decay probability density, so to say. And this is clear, but then the next question, which is more complicated, is the following. So suppose that we have an unstable state that decays in more than a single channel, 2 channels, for instance, and I consider the following questions: how to calculate the probability, let's call it Vi of t, that the decay occurs in the ith channel between 0 and t. So of course, the sum of the decay probabilities in all channels should be 1 minus P of t, because this is clear. But what about any single channel? And this is not a trivial question. So if I have n decay channels, so actually each decay channel has their own decay width function. If I go back to Breit-Wigner, it is a constant, but in general it is not a constant. The wall, so to say, loop self-energy is the sum of the n channels that I have. In the Breit-Wigner, of course, I go back to my constant, and the decay width is the sum of the partial decay width. So I go back to what we know also from the particle data group and from the various unstable states that decay in more than a single channel. There is a way to study that. There is a very nice so-called Friedrich-Lee Hamiltonian, which is, so to say, if I have an unstable state S, and some decay channel that are here enumerated from I going from 1 to n. So this is the transition of the unstable state to the final decay channels. So this is, by the way, this model is used in optics. It's called James Cummings. It is what it was used in atomic physics. It was rediscovered in as a model of quantum field theory. It is the same everywhere, just in different, with some slightly different ingredients. It's very general and is exactly solvable because it is linear. So the probability of decay in a given channel at the time t, so the probability that the decay is occurred, let's say, in the first channel between 0 and t is just the sandwich of the initial states with the final state in that channel and the evolution, time evolution operator. And the final formula, let me write it like that. So after one does the calculation, is here. So if we know this decay width function in the ith channel, we also can calculate the spectral function. Then we just have to do this integral and we have it. And so this is basically the solution of this problem, is a double integral. Everything is convergent here because there is no pole at E prime equal E, because there is also 0 here. So everything is well defined. And then, of course, I can also calculate the derivative of this probability Vi of t, and this is Hi of t, that is the probability that the unstable state decays in the ith channel between t and t plus the t. So it's the probability density in that channel. So let me do, so what if I go back to the Bright-Wigner? Do I get the results that I expect? Yes, of course. So this is the Bright-Wigner distribution, where gamma is the sum of all the partial decay widths. This decay probability, the survival probability is the exponential, and the decay probability in a given channel is just that decay width, the partial decay width divided the total times the total decay probability, which is this form. And these are the decay probability densities, they are just the gamma I divided gamma times the exponential. If I take the ratio of two decay probabilities in two different channels, let's say the first and the second, you get just a constant, which is the ratio of the decay widths, the partial decay widths. And this also applies for the ratio of the decay probability density. So the Bright-Wigner limit is very simple. What if we consider a model which is, so to say, non-Bright-Wigner, a simple one? So let's say the one in which the decay width function have this form. And this is actually taken by a paper, I mean, is inspired by a model of Facchi and Pascazio, where they model the decay in the hydrogen-like atoms. So the transition of the electron jumping down. So this would be the function. So you see, it is not it is not a constant. So it has an energy threshold. Each channel has their own energy threshold, and this is a square root. It's not a simple theta, but it's a square root. And then there is a kind of form factor, which is 1 over energy squared plus lambda squared. And this is the calculation. This is survival probability. One can see here the small 1 minus t squared region, and this is the probability of the decay happens in the first channel, and this is the probability that decay happens in the second channel. Of course, if I do the sum of the three, I get 1. So V1 plus V2 is equal 1 minus P. What it is even more interesting is to build the ratio. So the ratio is not a constant. So it should be a constant in the Bright-Wigner limit, but it is not in the general case. So V1 over V2 in the Bright-Wigner limit is a constant, but what we see is something that is not a constant. This is how in this particular models it looks like. And this has not been measured yet. So this is also my proposal. It would be very nice to consider states with more than one decay channel and check then these ratios. So if I consider the decay probability densities, so the derivative of this function of the decay probability, it is a similar situation. So they are also not, of course, not exponential. In the exponential limit, they are also exponential because the derivative of an exponential is an exponential. But in the general case, this is not the case. And again, the ratio, which in Bright-Wigner or exponential limit is a constant, is some oscillating function. So also here we do see these deviations. This is my result in quantum field theory, and this is also general. Of course, if I do also here some ratio of the decay in one channel divided the second. This is not a constant again. So this is basically the same feature also for particles. I mean, doesn't matter if it is QM or QFT. Again, this is not seen in any experiment, and this is what I would very much would like to see. And then let me go to my second topic, which is the decay of a moving particle. Actually, you would say, come on, we already know that. If you have a particle that moves, we just have to add the gamma factor as for the muons, and the problem is solved. And the answer is no, it is not like that. And it is a subtle answer. So why it is like that? So these are actually a paper with whom my work is very recent. It's just for a couple of months ago. And so first, if we do the same calculation, but for a particle, an unstable particle with momentum P, so I get the same Fourier transform. Okay, of course, this is not from minus infinity. This is if you have a Breit-Wigner. Otherwise, you have your energy threshold, but this can be included here. And simply that here in the exponential, instead of the energy m, in this case, there is just m squared plus p squared. So I take p in the x direction. And then I can calculate the non-decay, so the survival probability as before. And so everything looks fine. So what if we, for instance, look at a particle, if we take the Breit-Wigner limit, so the simplest case, so the distribution is a Breit-Wigner. So capital M is the rest mass, gamma is a constant, and it is decay width, so there is no energy dependence. And let's consider this unstable particle that, like this one, that moves with momentum P. What we expect? We expect to have a decay width which is reduced, so that the lifetime is longer, as we know from the muon, in this way. So this should be what we would expect, our result. So this is just the gamma factors written as function of P and the mass. Well, there is an important and subtle point. You know, a particle with definite momentum in the long life limit has also a definite velocity. And this formula is very simple, is written here. But in general, there is a difference, because a particle, an unstable particle with definite momentum is not actually a boost, because an unstable particle is like having different energy. So you have to decide if to all different masses, you give the same velocity of the same momentum, and this is not the same. If we consider an unstable particle with a given momentum, so an eigenstate of the momentum operator, this is the result actually. For the decay width of an unstable particle, so you can take a pion or whatever, with momentum P. So this is how it looks like. It is not what we would expect by just applying the gamma, so the gamma factor, so dividing by gamma. It is different. By the way, numerically, it is extremely close. Of course, if you take the expansion, the first expansion in gamma over m is exactly this one. But it is not the same. It's not the same. It is a different function. It's not that I'm not claiming, of course, that there is any breaking of special relativity. It's simply that this state is not a boost. If you do a boost, I say it in a second what happens. So if I take the difference, so to say, of the result minus the Einstein's formula, divided the mass, so this is a dimensionless quantity. So this is how it looks like. So for if P is very small or very large, we recover exactly the Einstein formula. There is a certain P max, which is square root of 2,3 times the mass, for which the deviation is the largest. But you see, this is the formula for the deviation. This is proportional to gamma over m at the power of 3. So if gamma with respect to the mass is very small, so this deviation is extremely small. So it is, so if I take a muon, the difference, even at the maximum, it is something like 10 at the minus 53 MeV, which is a ridiculously small number. So something that you will never able to see in any experiment. But if we take the Rho meson already, which is a broad state of 150 more or less MeV, and the mass is 770 MeV, so the ratio is larger, gamma over m is larger, then we are already something which is, of course, more sizable, still the decay is very fast for the rho meson, so we cannot really follow the lifetime. We can just see the spectral function.
What about the sigma meson?
The sigma meson it will be even larger, but the sigma meson, how would you study the decay of the sigma meson? I mean, how would you follow the time of the decay of the sigma meson? So the sigma meson is a gamma over m, which is of order 1, by the way. So the 0.500. So this is for hadronic physics. I mean, it is that meson that disappeared from the particle data group. It was there in the 80s, then it disappeared, and then it came back, and it was finally confirmed when it was possible to show that there is a pole in the complex plane. It is a particle whose existence is confirmed by the pole. There is no bump. There is no bump in any pion-pion scattering. There is some enhancement, but no bump. And it was confirmed by the fact that various dispersive analysis says that there is a pole in the complex plane. Still, in this case, I cannot really use for my case because definitely it's not a Breit Wegener, but we cannot really follow we cannot create it and check the time at which it decays because it simply decays immediately. So, and then the next question is, and you see, I'm well in time. What if you do a boost? Do we recover the formula then of Einstein? So if I take an unstable state and I don't give to the unstable state a definite momentum, I really give a definite velocity. So each element, each mass element has a definite velocity. Well, the surprising result is that actually the decay is 0. So to say, the particle if I have two observers, Alice has the pion, for instance, and Bob passes with a velocity minus v. So for him, the particle moves with velocity v. Bob sees the decayed particle. So if Alice sees the pion, Bob sees the two gammas. Or I mean, pi 0, then it goes to gamma. If I have a muon, if Alice has a muon, then Bob sees the electron and the neutrinos. So it says, how is that possible? The point is that being a stable particle is not something that is invariant by boost. And this is something that I think is also connected to what the discussion of yesterday. I mean, boost and observer, this is a subtle things in quantum mechanics. But I would like to show a simple Gedanken experiment in order to show that. So suppose, let me take a neutron just, I mean, not for any particular reason, just because we are used to think as a neutron as an unstable state, the lifetime of more or less 10 minutes. So suppose that I put now the neutron, I localize it, but I localize it in two different places. So at 0 and minus L. So there are two wave packets, so to say, here. So at time equals 0, I have half of the neutron is here and half of the neutron is here. So this is its wave function. So of course, if I consider the time evolution in the Alice frame, after a long time, capital T, much longer than 10 minutes, I would have the proton, the electron, and the neutrino here, and also here. But what is the system as experienced by an observer, which is moving with velocity minus v? So for Bob. Well, for Bob, so this is the contemporary line of Bob. So at time equals 0, for Bob, there is a neutron here, and there is a proton, electron, and the neutrino here. So, and then you see that, so this explains why actually a boosted neutron for the second observer, in this case, is half a neutron and half is a decayed particle. It's already the proton, etc., plus the decay products. So this is simply because that what it is contemporary depends on the observer. So this is just a simple consequence of that. I mean, one can also see it here. So actually, all the things depends. I mean, I have to prepare wave packets in general. This is clear. So this is just so to say. So I just take a long distance between the two boxes. But if I have a wave packet whose extension is delta x, which is written here, if this delta x is small, so this is in the reference frame of L is, of course, so we have let's start time equals 0, we have a neutron, and then after a certain time it decays. For Bob, it is the same. So if delta X is small, of course, then both observers agree. But if delta X is large, then for Bob, the neutron is a superposition of being a neutron and being a decayed neutron. So it is exactly like this, just that it is now for one wave packet, but it's the same thing. So it shows that actually, if we take a wave packet and we do a boost, a bit of the neutron is decayed for Bob. How much? That depends how large is this wave packet, so to say. And so I go already to my summary. My point here is that, of course, we only put the velocity here, so the boost. So the next is, and we were thinking about that, it is a much more complicated problem, is what if I take a particle with an acceleration or in a, so to say, in a gravitational field. And this is, there are some papers, actually was discussing with George about that. There are some papers, and the problem is even more complicated in this sense if I put, so to say, an unstable particle in such an environment. But first we wanted to understand what if we do a boost, so to say, which is something that should be very simple, but it is actually not. So a boost is not does not keep the notion of unstable particle invariant. So this goes to my summary and outlook. First point, so the take-home message, the decay is never exponential. This is clear. This we agree. Although we still didn't measure that besides the two experiments that I have shown. So it is definitely, I think, something that it should be seen in other experimental frameworks. One thing that I propose is this multi-channel decay, so to check particles that have different channels and check the ratio of the decay in one channel over the second, because that is a nice way to see these deviations, because that enhances this effect, which is usually very small. Then the last part, the second part of my talk, I've shown you, so the decay of a moving particle, and so there is an interesting link between quantum mechanics and quantum field theory, and this is also, so to say, I think an interesting thing to look at. And for a particle with definite momentum, there is a different formula, and a boost is a subtle operation. So this is my conclusions. There are other references. Thank you very much.